Today we're going to run hypothesis tests for proportions. Our primary example today, well, first of all, you can go to this link and you can watch the general concept of a hypothesis test. But in our general example we'll start off with, we have the manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Okay, so the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food is our parameter. Based on store records, the proportion of customers who had to wait longer than 2 minutes was P is equal to 0.63. To reduce this proportion, the manager assigns an additional employee to assist with drive-through orders. The manager would like to carry out a test at the 5% significance level. During the next month, the manager collects data on wait times from a random sample of 250 drive-through orders and finds that only 141 of the customers have to wait longer than 2 minutes. So notice we've underlined key information as well. When we are looking at the hypotheses, these are working models that we adopt temporarily in test. We have two types of hypotheses. The null hypothesis is our assumption of the parameter, denoted as H sub O. The alternative hypothesis is the value of the parameter we consider plausible if we reject the null hypothesis. It's denoted as H sub A. The null hypothesis is always set equal to the proposed value. So in our drive-through example, we were given P equals 0.63. The alternate hypothesis is either less than, greater than, or not equal to. If I'm in the drive-through and I elect to have another worker, we want to, that should hypothetically have our proportion of those who wait longer than 2 minutes go down, which is why there's a less than sign. To test these hypotheses, we need to determine how likely our sample proportion is, assuming that the null is in fact true. To do this, we go back to normal sampling distribution, just like in the previous unit. So remember just the 4 steps we did with confidence intervals, we're going to follow those again. Same exactly. So the first thing, the state. What we'll do in this step is we'll state the hypotheses we want to test, the significance level, and define any parameters used. So our state, we're going to use alpha as the 5% significance level. Our null is P equals 0.63. Our alternative is P is less than 0.63. And P is the true proportion of drive-through customers who have to wait longer than 2 minutes to receive their food. The next step is our plan step. Here, this is where we identify the appropriate inference procedure and check conditions, just like with confidence intervals. So the name of this test is a one proportion z-test. It is random. We highlighted that 250 drive-through orders are randomly selected. 10%, 250 should be less than 10% of all drive-through customers. And for success fail, we'll do NP equals 250 times 63%, which is about 157.5. And our failures, 250 times 37%, which is about 92.5. And both are at least 10. Now we're ready for our do statement, do step. In the do step, we're going to identify the sample statistic, calculate the standardized test statistic, and then find the p-value. Okay, so the sample statistic is what happened in our sample. So our p hat, we had 141 out of 250 who did not have to wait longer than 2 minutes. And then now we're ready to find our z-score. Notice we are taking our p hat minus the null, right? So our null was 0.63, and then our standard error, 0.63 times 0.37 divided by 250 all over the square root symbol. You should get a z-score of approximately negative 2.16. Remember, we like to draw a picture next, and there's a couple pieces missing in our picture. Remember, it's a good idea to mark the mean and the standard deviation, 0.63, comma, the square root of 0.63 times 0.37 all over, that's a 7 by the way, all over 250. Okay, and it's also a good idea to mark our 141 over 250. Now to get our p-value, we're either going to use the chart and look up the z-score of negative 2.16 and write this number down, or we can use a normal CDF, our lower bound because it's a left shade, because that's what my HA is indicating. This is my lower bound, negative 1,000. My upper bound is my parameter, or not parameter, my statistic. My mu is the 0.63, and our standard error is the standard deviation. And notice we get a p-value that's approximately the same. The last step for us to do is our conclude statement. This is where we're going to make a conclusion about the hypotheses and context. Okay? So our conclude. Now remember, you can look at the poster in the front of the room for sentence frames if you need them. But since our p-value is low, meaning 0.0154 is less than 0.05, we reject our null. We have sufficient evidence to suggest that the proportion of drive-through customers who have to wait longer than 2 minutes to receive their order is less than 0.63. Okay, and they are extremely picky. They want something that looks almost identical to this. They want the same words, they want the p-value and the alpha value, they want the reject the null or fail to reject the null. The sufficient evidence piece needs to be there, the context piece needs to be there. I want you to next think of a hypothesis test like a trial. How juries decide on a trial. Remember, to prove someone is guilty, we start by assuming they are innocent, right? Innocent until proven guilty. We maintain that hypothesis until facts make it unlikely beyond a reasonable doubt. And then and only then do we reject the null hypothesis of innocence in favor of the alternative, which in this case would be guilty. So statistically, we test our hypotheses the same way, but we are able to quantify our level of doubt. A p-value is the probability that our findings would occur given that the null hypothesis isn't true. If the p is high, it means we didn't find anything unlikely or surprising, meaning we failed to reject the hoe. Note, a high p-value does not prove that our null hypothesis was correct. We can only say that it doesn't appear false, right? In a trial, if we have someone we're trying to show is guilty, we never say that, the jury never comes back and says they're innocent. They always say not guilty. Also, other critical things, if I see this p of a, remember that's equal to a probability. An italicized lowercase p is a population parameter, and the p hat is what is observed in the sample. If a p-value was low enough, meaning it's less than our alpha, it's very unlikely we'd observe data like these if our null hypothesis was true, and this means that we can reject the null in favor of the alternative. So in our next example, we have a research team wants to know if aspirin helps to thin the blood. The null hypothesis says it doesn't. They test 12 patients, observe the proportion with thinner blood, and get a p-value of 0.32. They proclaim that aspirin doesn't work. What would you say? So for our answer here, if we have a p-value of 0.32, they proclaim that aspirin doesn't work. So what we say is that we just can't conclude the null is true. You can say the experiment is unable to reject the null, meaning we are unable to show that the aspirin is effective. Let's look at number 2. An allergy drug has been tested and found to give relief to 75% of patients in a large clinical trial. Now the scientists want to see if the new improved version works even better. What would our null hypothesis be? Remember, the null hypothesis is what we're assuming is happening in the population. So if we know that 75% of patients have received relief, that is how we're going to write our null. If we look at the last question, it says a drug is tested and the value is found to be 0.0001. What would you conclude about the new drug? So with the p-value of 0.001, we would say we have strong evidence to reject the null and conclude the new version gives relief to a greater proportion of patients. In our next example, we have Bellevue East makes a change to improve student satisfaction with parking. Before the change, 37% of the school's students approved of the parking that was provided. After the change, the principal surveys an SRS of 200 students at East. In all, 83 say they approve of the new parking arrangement. Do the data provide convincing evidence at the 5% significance level that the change was effective? This is a case in which we're going to do a hypothesis test. We know it will be a hypothesis test because it says convincing evidence in the story. So for our state step, we're going to say that P is the true proportion of East students who approve of the parking. The null would be P equals 0.37, and the alternative would be P is greater than 0.37, because we want to know if the change improved satisfaction rates. For our plan step, we're going to use a 1 proportion z-test with an alpha of 0.05. We are given here that the sample was random and SRS of 200 students. For a 10% condition, 200 students is less than 10% of all students if East has more than 2,000 students. Success fail, n times p, 200 times 0.37 is about 74, and 200 times 0.63 is about 126. So both NP and NQ are at least 10, so it's good to go on. For our do step, the first thing we're going to do is a z-score. We'll take 83 over 200. We're going to subtract our null hypothesis of 0.37. We're going to divide by the standard deviation. We'll take the square root of 0.37 times 0.64 divided by 200, and we should get a z-score of about 1.03. Next thing we'll do is we'll draw a nice little sketch. We'll notice we have our null hypothesis here as our mean. We have our statistic from the sample. We have our normal identification, and we have a normal CDF. The only thing that's missing is our labels. And if you use a calculator, you should get a p-value of about 0.1539. Now you could use your chart and then subtract that decimal from 1. The last step is to do our conclude statement. Yep.
So say most, is that going to be like 50%?
Yes.
Okay.
Use 0.5. Mm-hmm.
Did we not do one like this in the past?
Yes, we did.
Like,
For 13?
yeah.
Yeah, like these two.
But isn't that like backwards?
Huh?
Because it's saying like, if they work together, it's 2 hours.
You just fill out your table differently. Your X is a different place.
So the,
So our conclude statement, because our p-value was high, meaning 0.1539 is greater than 0.05, we fail to reject the null. We do not have enough evidence to suggest the proportion of students who approve the parking has increased. Take a minute and try the last one on your own. This is the answer we should get after trying the problem. Now you're ready to do your practice. Hooray! The end.